I am a bioinformatics engineer at Ancestry.com. My background has always been in biotech, and I tend to focus on the engineering side of that problem. So I build data pipelines for scientists as well as for production systems. I've talked to a few people who are working in biotech. Can I just get like a show of hands of people who are working with biological data? No one. Come on, really? All right. Well, hopefully this talk is interesting for you. It's not. It's more engineering focused, so hopefully I'll keep you entranced. Does everybody know what Ancestry.com is? I see a couple of hands. Yeah. Okay. Cool. I'm gonna give you the background anyway. This is my corporate obligation slide here. So Ancestry.com is a family history website. They collect genealogical records from a bunch of different sources, like census records or military records or immigration records, put them in a big database, and then our users are allowed to search those records to construct family trees. So we have over 20 billion of those genealogical records for people to search, and our users have then taken those to create over 100 million family trees on our website. About 7 years ago, Ancestry ventured into the consumer genomics space, and we released a DNA test where you spit in a tube and send it into our labs, and we'll give you two main products. There's actually more than this, but these are kind of the core of that product. The first is that we'll give you an ethnicity estimate. So we'll tell you kind of like a breakdown of where your lineage comes from. In this case, this person has mostly Eastern European DNA. We render that on a map to show the different areas where you might find your origins. The other piece that we do is we provide a matching algorithm that detects who else you might match to in our database. So you can see in this case, right, this person has all these other people who have also taken our test. They've gone through and pitched this product to the rest of their family, clearly, because they have both their parents as well as a sibling. And this was supposed to be more of a reveal, but it's in the title of my talk, so it doesn't have as much impact. But we have over 15 million of those DNA tests, right? So when you take this test, we search through that database of people and connect you to people that you're related to. And since this is a data science conference, I know the question that's on everybody's mind, which is 15 million DNA tests. That seems like a lot of spit. So we do have a spit test. I'm here for you to provide this information. So that equates to about 4,883 gallons of spit, which is kind of a hard number to really think about what that means. So I've also got you there. That equates to about 61 bathtubs full, and that's like an 80-gallon tub filled to the brim, so you could actually probably take more baths if you want. And this is kind of gross because we're all adults, and who takes baths, right? We take showers, right? So this would also be a 38-hour shower in pure spit. Yeah, I know you weren't expecting this talk to be so gross. And I think if anybody remembers anything from this talk, this will be the slide. The other thing to mention here is that I did all of the artwork here in Google Slides, so these are originals. I'm really proud of my bathtub guy. He looks like a little dejected too. Anyway, so I mentioned most of the talk is going to focus on production data pipelines. I'll kind of clarify what that means a little bit, but I'm going to try and tell the story of our DNA pipeline and kind of give the history of that pipeline, as well as the sort of technical decisions that we made along the way and how some of those were missteps and how we kind of corrected those, and kind of give a bigger picture of how implementing pipelines with simplicity is is the ideal approach. So when I mean a production pipeline, I'm kind of trying to draw the line between these two groups, which I think is probably a relationship at a lot of companies where you have an R&D group who's focused on algorithm development and building models. And I'm guessing most people in here from the talks I've seen are more on this side of the fence. Is that accurate? Who's doing more R&D type science work? No? Okay, there's some people, yeah. On the other side of that, we have the production engineering team who's taking those algorithms and models and implementing them in a way that works at scale, right? So we need to, okay, good, yeah, cool. we got some people from both sides. So most of my background is actually on the production engineering side of things, working with biological data. I've since moved into the R&D side, so I have a little bit of both worlds here. And actually, like, if someone's looking for a talk to do who like knows this relationship well, I feel like this would be like a really interesting space to explore, just like from a, you know, I don't want to say cultural, but like how those two teams interact. I think it's an interesting kind of problem of like two groups who have very niche areas of expertise that have to work together. So this is the pipeline I want to talk about. As I mentioned, when you spit in that tube, it gets sent to a lab, and we have a third-party lab partner that processes all of those samples. And then they send us basically like a text file that contains the DNA information. And that's literally just a text file, and it's ATCGs with an identifier attached to it. And that enters basically right into the pipeline. And I just generally call it the pipeline because it's easier. And we have three main things that pipeline has to do. The first is that we do some sample QCing. So we need to make sure that like the sample didn't, get contaminated in the lab, or like when the person spit, they spit enough, and we have enough data to actually analyze it. And then we run those two core algorithms. So we run that ethnicity algorithm, and we run that matching algorithm. Those results that we generate from that pipeline get sent off to a separate database that another team manages. And so this kind of like is maybe a little bit different than people who work on typical production systems think about, where if you're working on a production system, you think about things like scale and load as the issues that you're trying to tackle. This pipeline doesn't really concern itself with load so much. It's more trying to beat the clock. So every day that lab is sending us data, and we have a 24-hour window with which to process that data and then deliver results, because otherwise we become the bottleneck of that system and can get caught behind, and then customers get mad because it takes months for them to get their results after they've spit in the tube. Does that make sense, kind of? I hope. So jumping back to the beginning of when this pipeline started, it kind of started like a typical bioinformatics pipeline, which is that it was a Frankenstein mess of like Perl and Bash code, as well as like a bunch of research tools that were out in the wild. So we used two primary tools that are actually just out of different universities. There's this admixture algorithm, which is what we use for our ethnicity detection. That's just a supervised learning algorithm from Alexander. And then we run this germline algorithm, which detects matches in a group of people based on their genetic data. And that's out of the Gusev lab. You can tell which tools are the research and academic ones because they get no logo, and I had to use Courier to further shame that tool. So when we had this pipeline pretty early on, there was a couple of big challenges that we had with it. The first is that we had set this all up and it ran on a single machine, right? And we realized, like, even before we had launched the product, that just wasn't going to be tenable for long term. So we needed to find some way to distribute that processing across a bunch of different servers, right? Which is a common problem. The other thing that was really a driver for us, like an extreme motivator for us to make changes to that Perl and Bash pipeline, was that the germline algorithm itself has a quadratic complexity to it. And I'll explain what that means, and we'll dive a little bit into how that matching algorithm works at a very high level. But these were the two kind of core problems that we were trying to solve as a company once we had this kind of like prototype pipeline that we then needed to build into something that was more like a production system. So this is going to be kind of like a poor man's genomics 101, as well as like an introduction to how our matching algorithm works at a very high level. Everybody has two copies of DNA, one from your mom, one from your dad, right? And so that's represented here. Sample A has, dad's DNA, mom's DNA, and sample B has dad's DNA, mom's DNA, right? And what we're looking for in matching is just sections of DNA that are identical between those two people, which would indicate that they received that DNA from a common ancestor or like a parent, right? So in this case, again, it's kind of hard to see, but these two sections of DNA are identical, so we would identify those, and then we kind of sum up how much of that DNA is shared between those two people, and that actually gives us an idea of how closely related they are. So if you think about it, if that amount of, this is a simplification of it, but if you had 50% shared between sample A and sample B, that might indicate that it's either like a parent to child relationship or like a sibling relationship. So it tells you how far removed you are from those other people. Is that hopefully a kind of quick introduction to that? It's basically like a specialized like string matching algorithm, right? We're trying to find these common sections of strings between two samples. And this portion of the algorithm is not particularly like complex. And from a computational perspective, it's actually pretty quick. The quadratic nature of it comes when the implementation itself behaves like this. So if you imagine that you had a database of, say, 4 people, which is much smaller than we have, but it's easier to visualize, you need to draw connections between all of these samples. So we need to do that string comparison between sample A, B, C, and D, right? Pretty straightforward. And if we also need to go through all the other samples. So B gets compared to C and D, and then C gets compared to D, right? And the germline algorithm works like this, and it takes a single input, right? So if you imagine you're in a research lab, that works really well for you. You have a bunch of data that you've gathered, and you just want to run and find all the matches between that data set. For a production pipeline, this became really limiting because we get the answers to all of these questions on day 1, and then we get another sample that comes in, right, that we need to perform matching on, right? And the problem with this implementation is that it then has to rerun all of those other comparisons again to answer that one question. So if we wanted to find out, we already know who A, B, C, and D match to, and we just want to find out if E matches to those people, we have to rerun all the comparisons again. So this is kind of like if someone added a new web page to Google or to the internet, and Google, instead of just like indexing that one web page, they just re-index the entire internet, right? So like I said, from a research side, that algorithm is actually like, it makes sense in its implementation, but for our production systems, it wasn't going to work. It wasn't going to scale. And we could actually predict that. This is a graph of like the projected run times of that algorithm. And some of this is actually the true thing. So this was, again, on a quadratic scale. Our head of science, Kathy Ball, used to say that she could pick the day that she was going to get fired because this would run over that 24-hour time limit and we wouldn't be able to continue processing samples anymore. So this was a high priority for the company and for the product as it grew. So we made a decision that I think a lot of companies made back in that time, this is right around 2012, and decided to use Hadoop. So as I mentioned, we needed to solve that single machine problem, and that's what Hadoop was doing for us, right? It allowed us to take this problem and parallelize it across a cluster of computers. And we went like all in on this. We took that whole entire pipeline and rewrote it from scratch, and it actually took about a year of time to do that implementation from the time that we decided to pick that technology until we had released it in production. And like I said, it was a big investment. You can actually go online and there's talks that dive a little bit more into how the internals of that matching algorithm work that are fascinating to look at in this context. The other thing is that so we re-implemented that germline algorithm in Hadoop natively and allowed it to take 2 inputs instead. So we could then, rather than having this like single database of things, we could say, here's the database of all the samples I already know the answer to, and here's the new sample that I want to find matches for, right? And so this makes that problem be linear instead of quadratic, which is great. The other thing is that someone decided to call this algorithm also germline, but with a J, which is by far the most confusing part of this talk for me. I have to refer to this algorithm as J germline from here on out, so I apologize for that. Anyway, I think the J stood because it was written in Java. So like I said, this is great. It really solves that scaling problem for us, as well as we have this implementation that we don't have to worry about that ceiling of like getting to the point where it's going to take 700 hours of compute time to process 60,000 samples. And like I said, it works. So this is a graph of when we released that product. And you can see the quadratic nature of the runtime and then the drop when we released that. You can also see just how close we came to the 24-hour mark of releasing this, which is a little bit terrifying. And this is actually, it looks pretty flat here, but this is actually linearly increasing in runtime as well. It's just not zoomed out far enough. So all of this part of the story kind of predates my time. I started working on this production pipeline team about 2 years later. And when I came in, I thought that this was going to be like I said, my background's in biology. I was like, this is like the Burj Khalifa of like biotech pipelines for me. I was like, this is going to be awesome. I'm going to finally like use Hadoop and like work with this cool data set. It's probably the largest set of genomic data that I had ever worked on. But when I came in, the implementation felt a little bit more like this. It was like still kind of an impressive feat of engineering, but there was just like something fundamentally wrong. That analogy is like really on the nose. I apologize. So I want to walk through like what the problems were with that pipeline, right? We had an implementation that worked and it solved our problem for us, but there were other issues that came with that. So the first thing I want to talk about is like how that pipeline actually ran. These are kind of made up times, but just because I don't remember how that schedule actually was. Hadoop is a batch processing system, and I think a lot of people run it on a schedule, right? Like you have a job and you want to run it at every day at 12 p.m. or whatever, right? It's a pretty common pattern. We were actually using a tool from LinkedIn called Azkaban, which is designed to run scheduled Hadoop jobs. And so, this is like how the flow of the data went, right? At 4 a.m., the lab would start delivering data. And at 9 a.m., we would kick off QC and matching and so on and so forth. And scheduling has some inherent problems, one of which is that like you have to kind of over allocate your time, right? So if we know that QC is going to take about 2 hours, we want to give it like a little bit of extra like time to run. So we actually had a cluster of like 50 servers running to process all of this data. And as you can imagine, like any sort of like idle time is a little bit wasteful. The other thing about batching is that in a production system in particular, the longer something runs, right, the higher the risk of failure becomes. So if you have a job that takes 2 hours to run, like in this case, we're running our QC thing, and it's supposed to take about 2 hours and it fails an hour and 45 minutes in, that means we have to start all the way from the beginning and we've just lost an hour and 45 minutes of processing time. In this example, you can imagine like matching takes 6 hours to run. If it fails 5.5 hours in, then we're actually like bumping ourselves back into the next day and we've already lost that time. So this has like a couple of issues. We end up kind of like also getting uneven amounts of data from our lab. Some days we'll get 20 samples, other days we'll get 5,000. And so our days end up looking more like this, where we're all sitting around in a room and I have a team of 5 developers, and rather than writing code, we're all talking about how we're going to run the schedule for the day. We have to figure out, we received this many samples last night, or how long is matching going to take approximately? Let's add a little bit of time and make sure that we're not going to have that thing fail or run into our ethnicity run or whatever it happens to be. And this is like further complicated by the fact that Hadoop kind of requires like a little bit of like hand-holding in those situations where you're having uneven amounts of data, right? You have to kind of twist the knobs a little bit and adjust memory and adjust the number of mappers and things like that. So we're spending a lot of time doing things that I don't typically want a dev team working on, right? It's like we're doing more hand-holding of this pipeline rather than trying to automate these problems and find different ways to go about them, or even focus on other more important issues. So those are kind of like the inherent problems that we had with Hadoop as a solution. The other thing that started to happen was that Ancestry's DNA test started taking off. You can actually see, there's a couple of like little bumps in the amount of samples that we're receiving per day. And this is kind of like Ancestry became, or well, more specifically, I became a victim of Ancestry's success here, where we started kind of seeing the properties of that pipeline kind of stretch. And we were realizing that we weren't going to be able to run the pipeline in that 24-hour window anymore. And we found that out somewhere in the middle of like 2015, where it like really had started to take off. And so the nice thing is we're in Hadoop, right? So we know that we have a scaling problem and we're going to run into that wall, so we can just buy more servers. And so that's what we do. We figure out that we're going to need to actually double the size of that cluster if this rate continues to make it through the end of the year to continue that processing. So I don't know about you, but typically if I ask for 50 servers, and these servers were like 24 cores or something, so that's like 1,000 cores, you have to really justify it. And we could justify it in the sense that we could say, we're hitting this 24-hour window. If we want to keep running this product, we need to invest in it. But they also understandably wanted to see that we were fully utilizing the hardware that we had. And that's where it became a little more problematic. So This is a CPU usage graph of like in the middle of a germline run. As like kind of an interesting aside, you don't have to count them, but each of these little peaks corresponds to each of the chromosomes that we process. So we process one chromosome at a time. Chromosome 1 is bigger than the other one, so it goes along. Anyway, we only use 22 of the autosomal chromosomes. Nobody did sorry, nobody did biology, so maybe this doesn't make any sense. And then the end is kind of the reduced step. So this graph became kind of problematic, mostly because we were trying to justify that we needed more hardware. And if you average this out, it turned out that we're only using about 30 to 35% of the CPU to solve this problem. So we're asking to double our hardware when we're only currently using about 30% or a third of what we already had, which again is an issue. And so we started to try and dive into this problem. And this is where I guess like the complexity of Hadoop started to kind of become a burden on us. This is an iceberg, by the way. So this is one of my other art originals. And it wouldn't be a tech talk unless there's like some iceberg imagery. So the problem is we started to look at optimizing this problem. And the thing is we had a pretty straightforward implementation of that string matching algorithm in our germline code. And there wasn't really much we could do. Like, we can't change that algorithm because like that's the gold standard of how we perform matching. But we had this like whole other hidden part of how Hadoop works. And it was like really hard to start debugging and diagnosing what was going on to cause the CPU to be idle for most of the time. Is it some problem with like how HDFS is like delivering data? Do we need to tune that? Is it like how Hadoop itself is like partitioning the data across this cluster for us? And it became like really hard to dig into those type of questions. And this gets further complicated when our R&D team had also been hardly working away at, that was the wrong phrasing for that, working hard at developing a new matching version. So they had taken some new research and had tweaked this algorithm for us. And as you can imagine, they have their own implementation of this algorithm, and now we have ours. And they've made changes in their code base, and we have to then translate those changes into this Hadoop implementation. And this actually ended up taking about another 6 months of work for us to do, which is like an immense amount of time, given that, like, so we've already invested that first year to build this system, and now like the maintenance of it is starting to bite us as well. And this kind of like harkens back to that same iceberg image where it's really hard to develop things in Hadoop, right? We have all of these other things, other components that we have to set up even just to start developing in those systems, as well as like then being just like harder to test and debug and like work in isolation with those solutions. And so this actually kind of, for me, became the straw that broke the camel's back a little bit. We were taking so long to develop this algorithm that it started to impact product timelines where other teams were ready to deliver this and were just waiting on us to finish the actual core algorithm to deliver, which is, I mean, not a position that anybody wants to be in. And so with the sort of like combination of these problems, we decided we needed to do something simpler, which is when we decided to switch to Python. So at a very high level, this is kind of like the pitch that I gave to, I guess, the company as we made this decision about why we wanted to do this. And these are probably pretty common explanations, I think, of why you might choose Python for a solution like this. One is that it gave us a common language with our R&D team. A lot of our R&D team was working in Python as well as R, but it gave more of a possibility that we could share code with them when they developed algorithms or tools or whatever it happened to be that we could then leverage in our pipeline. As everybody here, I hope, knows, we're at a Python data conference. There's like a rich data tool set and language features in the language itself that make Python well suited for dealing with a data pipeline. And we wanted to be able to leverage those tools in a cleaner and easier way than what we could do in Java. This is actually, like, I think maybe a common one. One of my coworkers used to say this all the time, that Python is good glue. And we're building a pipeline, which at the end of the day really is that we're like taking together different pieces of like disparate technologies and kind of chaining them together with, hopefully like lightweight glue in between. And Python works really well for that. It also allows us to, do an implementation in a different language when we need something more performant. And then the last thing is that it's simple. It's simple, right? everybody knows that Python is a simple language. This helped us remove all the complexity that we had in that Hadoop system and instead just write very basic Python code. So I'll talk a little bit more about how we actually did those things. The first thing that we wanted to address was we wanted to move away from this scheduled and batched model. And we used a technology for that called Celery. So I was actually surprised when I asked people before, who here has used Celery? Okay, maybe not as many as I thought. Has anybody not heard of Celery? And you don't have to be shy. Okay, cool. So I'll give a lightweight kind of explanation of what Celery does. Celery, I think most famously, is used by Instagram. They use it as their back-end processing for all of their images filters as they come through. But Celery works like this. You have a queue and a cluster of workers. And on each of those workers, you load up all of your code that you need to potentially run. And then to execute that function or code in Python, you just send a message into the queue with the function name and its arguments. And there's not much more to it than that. It's pretty straightforward implementation of this. It's probably a common thing for people that have used other queue-based technologies, even Slurm or other things like that deal with some scheduler that reacts to an event coming in. And the other thing that we did with this, so this kind of makes it so that instead of waiting for data to come in or figuring out when something finishes, we then react to that data instead. And then there's an event that happens when matching finishes, we send another message back to the queue to move on to the next step. The other thing we do is that we break this up into more of a single sample processing sort of model. So instead of doing batches, we're processing one sample at a time in each of these functions. And we also further break that down into individual pieces of those steps, right? So rather than having this QC portion of the pipeline, QC is really three, this is again, just an example, but 3 different functions that we run. And so this solves that problem of batching incurring risk, right? So now if this validate step fails for sample C for some reason, maybe there's an integration with some API that we need to call to validate and it breaks. The rest of the samples just continue marching on and finish their work. And we can retry that sample, and it also has a larger impact on how much time is taken away from other things working, right? If we retry that, hopefully that function can run in just a few seconds, and we've only lost a few seconds in the event of a failure. And so for the people that this is also very simple to implement. And again, it almost feels comically simple compared to how you have to deal with Hadoop. If you imagine in Python, you just have some function, right? And in this case, again, these are contrived examples, but we want to QC some sample, and it's a Python function. We do something to check, call rate to make sure the sample looks okay, and that, I don't know, heterozygosity and all these other things that, again, maybe don't make sense to anybody. And it's code that we can run on our laptop. We can run it on a cluster, and it's all the same. And that makes that much easier to work with, as well as debug and check for problems and optimize for. If we want to put this in a Celery application, it's basically 4 lines of code. We create a Celery application, point it to our queue. We annotate this method with a task, which kind of wraps that as a Celery function. And then if we want to call it, we just say, call that function and delay with the arguments. And that sends that message off to the queue, and then the workers can pick that up, process that data, and they can send back results. Celery also has sort of built-in monitoring and automatic retries for us. It's a very full-featured sort of solution, but it also has a very sort of simple architecture to it that it makes it, like I said, very easy to work with. So this is continuing my sort of contrived example. This is a glass of water with a physics-defying ice cube in it, where we now have mostly our code. So we've moved all this other stuff into Python functions and some C++ to optimize certain parts of the pipeline. And then we have this very thin layer of Celery that we don't even really have to think about from a performance or debugging perspective. It's just kind of the orchestration layer that we use to submit these things to that. But it doesn't really interfere with how our code runs. So there's a lot less for us to think about. So that's kind of how we solved this distribution problem, right? We we now have a system that we can is more event-driven, as well as avoids this batching problem. And instead, we have like a bunch of tiny little functions that run, and we reduce the risk of failures there. So then we come back to that other problem, which was that quadratic matching issue. So we want to move away from Hadoop, and we want something that's hopefully a little bit more efficient. I think a lot of people think about, this is maybe an important distinction to make. We're often told that Hadoop is a fast processing system, and it is, right? Like, the horizontal scaling allows us to take a problem, distribute it, and then process that problem quickly. But it's also pretty inefficient. We're dealing with a lot of layers of abstraction, and it tries to hide those pieces from us, which is great. But it also makes it so that it has to make a lot of assumptions about how that data is run that is like maybe hard for us to dial in. So instead, what we want is something that's a little bit closer to the metal, a little more optimized, ideally something that's written in C++. And it turns out that we already have something that does that, which is ggermline. And ggermline, I kind of glazed over, is an open source project. And so what we really need to do is go into this open source code, change it so that the implementation allows us to pass in 2 arguments instead of 1, so that we can do our new samples compared to our old. And then we get a C++ implementation of this algorithm that can run in Python code. Our Python code to implement this is 10 lines to call subprocess.run and parse the output for it. This also has the added benefit that the research team is also coincidentally already using this C++ code. They've already implemented that new matching version for us. So now our work to take that code from R&D land into production is to replace an executable and then test and validate it. And that's the extent of implementing that new thing, rather than this being a 6-month project for us. So the other thing is that this is now much more efficient. This is a CPU graph during a germline run. You can actually notice that there's like a little bit of a gap, and that's just because we underallocated the worker for this because we were testing. But this actually pegs the CPU for the entire run of our matching things. And this ends up being much faster. It's actually about 64 times faster than the Hadoop implementation was. A job that used to take 6.5 hours now takes 6 minutes. And if you're good at math, we ran a 50-node cluster. This is so fast that we don't even need clustering anymore. We could run this whole algorithm for all the samples at the time on a single machine because it's so efficient. And actually, like, we probably could still be in a vertical scaling solution even with 15 million samples, but we're probably pretty close to that point where we're hitting that 24-hour window now. So yeah, this is much more effective. So you might be thinking to yourself, isn't Python slow? And I got this question a lot as we tried to move into this technology. And I feel like our answer to this should be the obvious one, which is yes. Python is a slow language. And I'm kind of cheating a little bit by saying, oh, well, like we're switching to Python for optimization purposes, when really I'm just like taking these core pieces and moving them into C++. But I think that like for 90% of the problems that we deal with data in particular, the language itself is not the limiting factor for performance. Very rarely are solutions driven by like a language itself, and instead it's the implementation that is slow. And Python is nice because it's so simple that it allows us to clearly see those problems and then address them in the implementation rather than as a language thing. We could do all of this in Java, but it would be a lot more code, and we might then introduce issues where our implementation is slow and we wouldn't see those things. And I'll give some examples of that, or kind of try and demonstrate that. So we had about 125,000 lines of Java code in this Hadoop pipeline, which is a ton. When we migrated the rest of this into Python, we had about 25,000 lines of Python and C++ code. So that's 100,000 lines of code that we don't have to test, we don't have to maintain for updates. And it's also just 100,000 lines of code that we don't have to like think about and like mentally map as we try and understand the system. It's still a big pipeline, but it's much smaller. And when we try and do these changes as we move things into Python, we found that we were actually writing things significantly faster than they were written in Java. Across the board, that's kind of a weird animation, the pipeline itself goes anywhere from 3 to 70 times faster for all steps in that pipeline. So the 70 times faster is actually just taking a pure Java code at part of the pipeline, migrating it into Python with Celery, and nothing else. It's just pure Python. And most of that optimization came from realizing that we were using the disk way too much for I/O operations. And we realized we could move all of that into these like handoff in-memory operations instead, and it just became much faster. And we wouldn't have necessarily like seen that problem if we were so distracted by the other 100,000 lines of code that we had to deal with in that other system. So remember that like even though the language can be slow, it's really implementations, I think, that oftentimes anyway are what's driving performance for us. And the other thing is that, this also scales. So this is not a great illustration of this, I apologize, but in the yellow here is when we had this Hadoop implementation, and then in the green is where we switched over to Python. And so you can see that that trajectory of growth of this database continued to just escalate, and this system just continues to work and scale for us, and do it at a much more efficient and performant pace. I forget what this slide is. Oh yeah. So this is kind of like my little nuggets of pipeline wisdom for you to take away from this. I'm not sure I'm doing on time. Okay. So the first is this, that events are usually better than scheduling. There are some cases where I think we need to do scheduling, and typically those are things that are like based around time, like where you need to run a report for the day before or something like that. But usually it's much more efficient and effective to react to data as opposed to scheduling around it. The other one is to avoid batching, and this one also has some caveats. Generally, like I said, we increase risk as we batch samples or batch, data together. And if we can like break those up and partition them into smaller pieces, we are less likely to be impacted by failures. There are cases where batching is necessary, and a good example of that is like if you have a task that has a lot of I/O, like if you're loading a model or something like that, and it takes 30 seconds to load the model and then 10 seconds to process one sample, it's probably better to batch it like 100 samples together and process them all at the same time. That you still want to try and keep the batch size small, but you might not want to totally remove batching. Another one is to share code. I feel like, and again, maybe this is not as applicable for everybody, but when you have these two worlds of research and development and production engineering, there's often this tendency to think that the code that comes out of research can't be put into production. And there's some truth to that. Like we need to be able to validate that code and make sure that it can handle production workloads and stuff. But I still think there's like this incentive or this, I don't know what the word is, desire, I guess, to try and like re-engineer everything for production. And instead, I feel like if we instead tried to build tools that met the needs of both those teams, we'd be much better off just from a maintainability perspective. This one is kind of highlights what I said before. We want to focus on things that are efficient in software and not just like focus on speed as a metric. If you focus on efficiency, speed will come with it. But if you end up focusing on just speed, you might end up, in this case, not using 60% of your CPU for a process, which can just be expensive. It might not matter as much for offline, more like data science type pipelines, but in production systems, it's going to have a big impact. And then the last one is simplify, simplify, simplify. I'm going to kind of close with this quote from Maciej Sklowski. I don't know if anybody knows who he is, but he's a fantastic speaker if you haven't heard of him. He's also very funny. So one question, there's probably two questions that have come to mind. One, which is something that bothered me for a long time, is like, why didn't we just change our germline implementation in the first place instead of doing this whole rebuild of that system? And I think this quote speaks to that, right? We got so enamored with a technology solution to solve our problem that we kind of forgot about what the core of the issue was or how to solve it in a quick and easy way, right? And the thing is, it's easy to be sort of blinded to what that problem is when the solution that you're implementing works, right? I can't say that Hadoop didn't work. It did. We had great benefits from it, right? But at the same time, it was just kind of like an ill-suited solution for our problem. The other thing is that you're probably wondering, like, this seems like it's a talk a lot about Hadoop. Like, I don't really care. And Python is a simple language and has simple tools. So, like, why do I need to worry about this? And I think to some extent that's true, right? Python, as one of its tenets of the language, is simplicity, right? So we can say that we have some inclination to move away from complex tools, but they're still out there. And if you look at like the Python data science ecosystem, I think you can see that too. Even if we have a bunch of different tools that allow us to do our job, and most of them are simple, we're still kind of like inundated with choice. And it's sometimes tempting to pick a tool that is more interesting rather than focusing on one that is the simplest solution for our problem. Yeah, I think that's it. I just wanted to call out these people real quick. This is the team that mostly did this implementation. I just get the pleasure of presenting it. But this is members of both the pipeline engineering team as well as the R&D team who did a ton of work to make this implementation happen. That's it. Yeah, questions?
You want to bring the microphone to you?
I'm just curious to know if you guys took any stab at optimizing the core algorithm, maybe using some hash sets or...
Yeah, so I really glazed over a lot of detail there. The algorithm itself, well, so let me answer that first part of that question. On the production engineering side of things, we tend not to worry so much about the implementation of the algorithm itself because we can't really change how the algorithm works, right? Like, it's not our job to determine what might determine a match between two people. So we try to focus not on those problems. We do like read the code and like look at optimizations, but we can't really like flip the algorithm on its head and produce like good but not the same results. Like, it's our job to create parity with what the R&D team produces. The algorithm itself is like really optimized. It does actually do hashing across all those things to do lookups. So the first step of that algorithm is to build a hash table across all of the samples. This is actually like an interesting aside. We actually were using HBase to store those pre-computed hashes for all those locations so that we could quickly look up locations where they matched. In the G-germline implementation of that, we didn't do that because it was actually turned out to be slower to retrieve those things over the network than it was to just recalculate them. If there are talks online, and we actually published both white papers for our ethnicity as well as our matching algorithms and a couple of our other algorithms. So if you're interested in how those work, they're all publicly available. But yeah, they are fairly optimized. The algorithm itself does run quite quickly. We do, like I said, read the code to try and find any like sort of obvious like errors that might happen. But our R&D science team is like a bunch of pretty smart people too. So like usually they have done a pretty good job actually for their C++ implementations anyway. So.
Thank you for sharing. I have a question about Celery. I'm not very familiar with Celery, sure. But did you also try using the Dask or comparing the performance between Dask versus Celery?
We didn't. So I think, Dask, and I haven't actually used Dask. I only know lightly what it is. Dask is a distributed pandas data frame. Am I way off base there?
It's also, in that you could also calculate something in parallel. And also, you could calculate something from one node to another, passing the value from one node to another. Very similar with Celery, I think.
Yeah. So I mean, I think they do have different goals, and Celery, like I said, doesn't have anything to do with the computation on the data itself. It's really just like a way to do almost like remote execution of a function on a cluster, right? So they do solve different problems. We haven't used Dask. I think like that might come back to that same problem where if we wanted to use a technology like that, it might require re-implementation to put it on that technology, which is something that might be a good idea, but is also something we might try and avoid. We haven't tried that as a technology. I do think their goals are slightly different, but I also haven't tried it. So I'd be curious to talk to you more about it. Like I said, my knowledge of Dask is apparently like zero.
Okay, thank you. Because I'm also not familiar with Celery, but maybe I think they're very similar because in Dask you also could do the partition and calculate it in parallel, also passing value from one task to another.
Okay. Yeah, I mean, like I said, yeah, come talk to me, because like I said, I don't know enough, and maybe we can bridge that gap there. I'm not sure. Yeah.
Did you have to, so here your sample was all specific genome.
Correct, yeah.
And so you had many million samples, but then, and you talked about computation on those things, like for example, computing relationships and so on.
Yep.
Did you use a similar pipeline for that as well, or was the previous structure which you had to process that data somewhat better?
So you mean
So if, like, for instance, finding relationships between multiple samples, right? So the kind of processing you would need to do there is going to be different. So that's where you're going to share information between two nodes and so on, right?
Yeah, so again, there are pieces that I glossed over on this a little bit. So if you think about like that matching question, for us, like it's really like, it's not that we want to say, does this one sample match to 15 million people? We want to say, does like person A match person B? And we want to get that answer and then send it off. And so we really like don't attack that problem as if it was a whole database that we needed to get one answer out of. It's like we have 15 million questions that we need to ask and 15 million potential answers out of that. And so it doesn't really like, I guess, require internode sort of communication. We're really just like loading up what actually amounts to like a very small amount of data between two samples and then processing them. There are some pieces that we do change, and again, that we do actually batch together at a small scale to avoid I/O challenges. If you think about like if we got 1,000 samples in a day and we wanted to do one at a time against that whole database, that means that we'd have to load the 15 million people 1,000 times. And so instead we do like kind of these micro batches where we do 1,000 people against 1,000 people. And then that in that case, we would only have to read that database once to do that. But we only get, oh man, I'm bad at math, 150,000, no, 15,000
Yeah, I get it. Yeah. Okay.
like computation things that we have to do. But there's not like a need for any communication between those nodes. Yeah.
One more thing, like, is the representation here is it like all graph databases here, or is it something else?
No. So, well, we actually, for the storing of the results is, again, that's another team sort of responsibility. We just write those out in flat files and then they get put into a database. We don't currently use a graph database, but it is something that we've thought about exploring. On the R&D side, we've talked about it a lot more because we're doing certain things with the output of all of those matches. Like we're running Louvain community detection on those as well. And like loading that up into a graph database is really helpful for us to do that research. But currently this pipeline is literally just dumping a flat file out and then like pushing that into an API, and then that gets ingested into a database, but it's not a graph database right now.
Is any part of this the Python implementation? It's germline with a G. Is any of it open source or anything we can play with at home?
Yeah, so germline with a G is open source. Admixture is not. It's also not the algorithm that we use anymore. We switched to a custom version of an ethnicity detection algorithm, and that's not open source either, unfortunately. We do have the white paper, which you could read through, and it actually goes through a lot of detail about how that works. And that actually is using a hidden Markov model for that implementation. Mm-hmm. Admixture itself, like I said, is closed source, and I think there are some open sourced like recreations of admixture, but not the core algorithm that we used. Sure. But yeah, ggermline is open source and is like not an unmanageable code base. We have like slimmed it down and like I said, it's just string matching essentially, and it's I think it works out to something like 600 lines of C++. So it's not a daunting sort of implementation for us.
Mm-hmm. Okay.
Yeah.
Thank you.
Yeah.
Samples to you twice. Will that get exact the same results in your algorithm?
Yeah. So you would actually come up as like a twin to yourself. You can like submit multiple kits to a single account, and we don't distinguish between those two things. So you would, so I shouldn't say that. You wouldn't get exactly identical results because like some of those learning models are there's the potential that you're going to have like missing data in certain locations and things like that. I think like for matching, you should probably get almost identical results. For some people get, like literally hundreds of thousands of matches after they take this test, and you might like lose a couple of like the really distant ones or something like that, but in general they should be almost the same. We have like a quality control that requires that the data have a certain we have a certain missingness rate that we don't accept and things like that. So ideally they should be.
So even if the sample is sent to you in different time, and then when you run through the algorithm, it will still get.
Have you had different results? Is that
I
why?
just
Okay.
you just talk about like you have two inputs. One is the original data. It's like your original data training results from previous day, and then you have new sample. So that makes me curious about that question.
We do there are a bunch of like, I guess, complicating factors. The technology has evolved over those 7 years. So the people that took the test in 2012 get a slightly different set of genotype data than the one. But actually for matching, we have kept the set of the genome that we use for matching is consistent across all of those versions. So it shouldn't be, but again, like there could be, like the technology might be better at one location, in 2012 than it is today, or vice versa. And so there's like a little bit of variance that might happen there.
Thank you.
Yeah. Cool.
Okay, Tim Orme, thanks so much.
Yeah, thanks guys.